So this week in the Computability Theory and Applications online seminar, it's my pleasure to introduce Tim Lok Wong, who is currently at the National University of Singapore. And he'll be speaking to us today about arithmetic under negated induction.
Thank you, Linda, for the introduction. Thank you very much for the invitation, and thank you very much for coming to my talk. I'm honored to have the chance to speak at a computability theory seminar. I'm already getting nervous seeing Professor Lem, Professor Shaw, etc. around. To those who don't know me, I work in the model theory of arithmetic, so I know just enough recursion theory to let me handle my models. I don't think I can impress anyone here by talking about recursion theory, so I just talked about what I'm good at. I'll talk about models of arithmetic. There'll be some applications in reverse mathematics, which I hope is close enough to recursion theory to be of interest to some of you, or I hope many of you. Okay, it's good to hear that. So I will, during the talk, feel free to interrupt if you have questions. You can just unmute and ask questions, or you can, like Professor Lem did, send a message in the Zoom chat. I'll keep an eye on the Zoom chat as well. So the work I'm going to present today is joint work with 3 colleagues. First, Marta Fiori Carones, who's a researcher now in Novosibirsk, and Leszek Kołodziejczyk from the University of Warsaw, and Keita Yokoyama he's now in Sendai, Tohoku University in Sendai in Japan. Unless otherwise stated, all the results I'm going to talk about are from the 4 of us. Actually, Keita gave a talk in this CTA seminar exactly 1 year ago. This is 15th of December, 2020, on essentially the same topic. Okay, but naturally, his point of view is more recursion theoretic because he has the ability to do that. My point of view will be more model theoretic. And after Keita gave his talk here, we were able to make a couple of improvements to our results. So what you see today will be the improved version of the results. Okay, so let's get started. As stated in the title, the talk today is about arithmetic under negated induction. This is the main theorem of the talk. The theory WKO0 star in the language of second order arithmetic under the negation of sigma 01 induction eliminates set quantifiers. On the right of the slide here, I put up a quotation from the classic model theory text from Chang Kiesler, and it's supposed to be there to convince you that this main theorem is extremely valuable and gives a tremendous amount of information about the theories involved. As someone working in the model theory of arithmetic, I don't usually get to use these mainstream model theory texts. Usually they do not tell us anything substantial about arithmetic. So this is a nice exception. We will see in a moment that this is one of the rare cases when we can actually go to a standard model theory text and get some non-trivial information about theories in arithmetic, which is nice. The plan of the talk, I'll start by setting up some notation. I'll define or I'll remind you what induction is, what collection is. On the way, I will give you some motivation of this work as well. Then I'll talk about some known results about the weak Konig lemma that I will use when proving the main theorem. Then we eliminate quantifiers and talk about some consequences at the end. So let's start with setting up the notation. First order arithmetic, this is where I started my research. I denote the language for first order arithmetic by L1. It has 0, 1, plus, times, less than with equality with their usual arities. A quantifier is bounded if its domain of quantification is bounded. And a formula is delta naught if all its quantifiers are bounded. From that, we can build the formula hierarchy. A sigma n formula has n blocks of alternating quantifiers starting with an existential one. At the end, we have a delta naught formula. The dual of sigma n is pi n. The theory I sigma n has some basic algebraic axioms that I call PA minus. Then a scheme of sigma n induction, which says that any sigma n definable set which contains 0 and is closed under adding 1 must contain all the numbers. And PA is just a union of all the I sigma k's. It has all the inductions. Note that following convention in the model theory of arithmetic, I do not have exponentiation in the language, but I will need exponentiation in this talk. So I need to state it explicitly. So I use exp to denote an axiom which asserts the totality of exponentiation over I sigma 0, for example. Another theory, collection, I denote by B sigma n. As base axioms, it has I sigma 0, and it has a sigma n collection scheme, which says that whenever we have a sigma n definable multifunction with the bounded domain, then I can bound the codomain such that the multifunction remains total. This is what B sigma n says. And it is well known that these collection schemes is a form, well, they are a form of induction in the sense that they sit in between the I sigma n's. Okay, so the union, in particular, the union of all the collection schemes is also the Peano arithmetic. And it is known that this is a proper hierarchy. So we have implications one way, but not the other. And as I mentioned, I will need to add exponentiation. So I add exponentiation everywhere. It doesn't destroy the hierarchy, it stays intact. But you only see the exponentiation up to B sigma 1 because above that exponentiation, meaning totality of exponentiation, is already provable. So you only explicitly see exp below I sigma 1. And when I said I want to negate an induction axiom, I'm negating one of these theories. Or actually, these are all finitely axiomatizable, so I just negate these axioms. As a model theorist, when I say I want to understand these theories, I want to understand the models of these theories. So one insight that Kay put forward at around 1991 is that if we want to understand the model theoretic properties of these models, then we don't just look at what induction axioms that these models satisfy, but we also want to see what induction axioms that the models do not satisfy. This is traditionally, it is not done this way. For example, traditionally, there are results which says that if you have a model of, say, B sigma n plus 2, if you have this amount of induction, then we know that there is a proper sigma n plus 2 elementary end extension. Well, assuming that your model is countable. So if you have more induction, then you have a more elementary extension, so you have nicer model theoretic properties. If you have B sigma 10, then you have a sigma 10 elementary end extension. B sigma 12, then you have sigma 12 elementary end extension. But around 91, that's what Kay thinks. If you do not only know that you are, say, above B sigma 2, you actually also know that you have some negative information. You know that you are below I sigma 1, then you have more precise information, and that should tell you more about your models. That's his insight, and lots of the things I'm going to talk about will echo this insight. One example that I wish to start with is this one, which is where case insight originated from, is that if you have B sigma n plus 1, but not the next level of induction, not I sigma n plus 1, then all the countable models will have continuum many automorphisms to a maximum number of automorphisms, and they all have proper elementary cofinal substructures, actually many of them, infinitely many of them. So these models, if you are at the level of B, but not the next I, then your models are guaranteed to be very rich, lots of automorphisms, lots of elementary substructures. But this is not so if you are at the other levels. If you are at a level I, but not the next B, then it is possible that there is no non-trivial automorphism, no proper elementary substructure. Actually, if you start with I sigma n plus x plus not B sigma n plus 1, then it's possible to find a model in which all the elements are sigma n plus 1 definable, meaning that there is a sigma n plus 1 formula which characterizes that element. So such models are rigid, no non-trivial automorphisms, can't get any proper elementary substructures. So the two kinds of theories are pretty different. The B, but not the next I, they give certain kind of richness to the models. They must give certain kind of richness to the models, while I, but not the next B, you do not get that. Okay, so that's one example in first order arithmetic. The next example I'm going to give is in second order arithmetic. So let me first recall the notation or set up the notation for second order arithmetic. Okay, I denote the language for second order arithmetic by L2. It has two sorts, number sort, set sort. So the set sort elements, objects of the set sorts are intended to be sets of numbers. I view L2 as an extension of L1 in the sense that I have the symbols for the language of first order arithmetic on the number sort. And on top of that, I add a membership relation between a number and a set. We use lowercase letters for objects of the number sort, uppercase letters for objects of the set sort. Since there are two sorts in the language, a structure in L2 has two parts, a universe for the number sort and a universe for the set sort. Okay, the first component is always a universe for the number sort, second one, universe for the set sort. Then we can build the formula hierarchy in a similar way. A quantifier is bounded if its domain of quantification is bounded. So bounded quantifiers are always number quantifiers. A formula is delta 0, 0 if all its quantifiers are bounded. Then we define sigma 0 and pi 0 and similarly. And the superscript 0 is there to suggest that there may be free set variables in the formulas. If we are in first order arithmetic where we do not have the superscript 0, there may not be set quantifiers. Set variables. If we take the union of these sigma 0 n's, we get all the arithmetical formulas, or what I write delta 1, 0 formulas. These are all the formulas in which all the quantifiers are of the number sort, no set quantifiers. Then from arithmetical formulas, we can build the formula hierarchy again. We can build sigma 1n pi 1n, in which, for example, sigma 1n has n blocks of alternating quantifiers starting from an existential one, and all these quantifiers are set quantifiers. And at the end, I have an arithmetical formula. Similarly for pi 1n. We can also define the theories, say I sigma 0n, B sigma 0n in a similar way except that there may be set variables, in which case we just quantify over them universally. And with this definition, the whole hierarchy of induction axioms stays intact. All the implications remains true if I add superscript 0 to everywhere. And also the non-implications also remain true. Okay, so these are the definitions. The example, remember what I wanted to do. I wanted to demonstrate that if I know what induction axiom that the model does not satisfy, then I want to say that it has some model theoretic property that I cannot describe if I only know positive information, what induction it satisfies. And the example I'm going to talk about is about omega extensions. So an omega extension of an L2 structure is just an extension with no new numbers. So the only new things you can get are sets. So omega here does not suggest that the first order part here, that the number universe here is omega, is a true omega. It can be a non-standard model, but it only says that there can be no new number. So let's start with the I, but not the next B level. If we have a countable model at this level, I, but not the next B, and given any subset of the number universe, then Tausner tells us that one can extend this model to a model which preserves the induction axioms that you already have, such that this set that you picked from the as a subset of the first order universe can be definable in this omega extension. So any subset of the number universe can be definable in an omega extension while preserving the induction that we have. And this is provided we are at this level, I, but not the next B. And definable here is actually delta n plus 1 definable. Okay. So in a sense, this says that there are many omega extensions for countable models of this theory, I, but not the next B. And this is not true if we look at the other levels, B, but not the next I. Given any countable model of this level, B, but not the next I, one can always find a subset of the first order universe that can never be definable in an omega extension, preserving the amount of induction that we already had. So there aren't many omega extensions if we're at the level B, but not the next I, in a sense. This may sound a little strange if we remember what we talked about in the first order case. In the first order case is B, but not the next I. These are theories that guarantee the models to be rich. They have lots of automorphisms, they have lots of proper elementary substructures, etc., but they do not have many omega extensions. And that's consistent. Well, this not many omega extensions is true exactly because they have, if you are at the level of B but not the next I, then you must have lots of automorphisms. You must be very rich. So that if you choose an S which does not have many automorphisms, you will not be able to define it. For example, I can take S to be the, say, the graph of a bijection from the whole model to the standard natural numbers. Let's say this is my S. Then this has no non-trivial automorphisms, everything, well, it fixes everything. So there is no way you can have a model of B, but not the next I in which this is definable, because this makes the model rigid. So having lots of automorphisms restricts the number of omega extensions that you can have. So this again shows in a context of second order arithmetic, also we have in a sense, a split. In the levels I, but not the next B, B, but not the next I. One of them, lots of omega extensions, one of them, not many. Okay, any questions at this point? I think this is the introduction part. Okay, not at the moment. Remember, just feel free to interrupt if you have a question at any point. Okay, omega extensions. Why do I want omega extensions? Usually in reverse mathematics, omega extensions are used to prove pi-1 conservation results. Let me just briefly describe the logic behind these, the relationship between omega extensions and pi-1 conservation results. So well, it's a rather standard model theoretic idea that if every countable model of a theory T has an omega extension to a model of another theory T star, then T proves all the pi-1 consequences of T star. So it is just like the preservation theorem for universal formulas in model theory. So the proof is elementary, but this is just because in an omega extension, you do not change the number, so the arithmetical part doesn't change, so you get pi-1 instead of just universal consequences. The converse is in general not true as written, but there is a partial converse. If the models, if you satisfy the right theory, then all the countable sufficiently saturated models will have the appropriate omega extensions. And I have written a converse here. Sufficiently saturated here, I mean recursively saturated. And there are some additional assumptions as well. The stronger theory, the T star, will have to be recursively saturated, pi-1, 2 axiomatized, meaning it's a set of pi-1, 2 sentences. In this case, there is a converse that if T proves all the pi-1 consequences of T star, then every countable recursively saturated model of T, omega extends to a model of T star. In case you haven't come across recursive saturation, I have a definition here, but it is what you think it is. It says that all the recursive types are realized. But to say what types are recursive, we first need to identify formulas with Gödel numbers. So each formula is a natural number. A type is recursive if you look at the Gödel numbers of the formulas in the type, ignoring all the finitely many parameters that may appear in the type. If this set of natural numbers is recursive, then a type is said to be recursive. And a structure is recursively saturated if it realizes all the recursive types. So if a model is countable recursively saturated and satisfies the right theory, then it has all the omega extensions that it should have. This gives us a characterization, or in a sense, a preservation theorem for pi-1 formulas in terms of omega extensions. Except that I should just add here that it is still true that if I only know that the countable recursively saturated models have omega extensions, that's enough to give us the provability condition already. I don't need it to be true for all countable models. Countable recursively saturated models are enough because we have a recursive language. Any structure can be elementarily extended to one that is recursively saturated of the same cardinality. Okay, so this is how we can use omega extensions to help us prove pi-1 conservation results. Okay, if we want to prove that a theory proves the pi-1 consequences of another theory, then we try to build omega extensions. Okay, from the first theory to a model of a second theory. One of the popular applications of this method is when people look at the Ramsey theorem for pairs for two colors. So let me just quickly recall what this is. I believe most of you know this pretty well. I denote this by RT22, just the usual Ramsey theorem for pairs with two colors, which expresses whenever each unordered pairs with numbers given exactly one of two colors, there is an unbounded monochromatic set. A major open question that is still open, I think, is whether B sigma 02 proves all the pi11 consequences of RT22 over the usual base theory RCA0. That it doesn't matter what RCA0 is for the purpose of this talk. So it's about whether a theory proves all the pi11 consequences of another theory, so we can reformulate it. All the theories here are pi12 axiomatized, recursive, so we can reformulate it in terms of omega extensions. This question is equivalent to asking whether every countable recursively saturated model of B sigma 02 omega extend to a model of RCA0 plus RT22. It's just using the preservation theorem for pi11 formulas that we saw on the previous slide. This is just a reformulation. The original question is still open. This version is still open, but there is a partial answer from Cholak, Jokush, Lehman, that if we have a little more induction, not only B sigma 02, if we have I sigma 02, this is the next level up, then the answer is yes. So whenever I have a countable recursively saturated model of I sigma 02, then I can omega extend it to a model of RT22. Actually, we don't need recursive saturation. And in the extension, we have I sigma 02 as well. But we have a positive answer for this question if we have slightly more induction. So the remaining question is, if we do not have this more induction, we do not have I sigma 02. Okay, is it true that if we have a countable recursively saturated model of B sigma 02, not I sigma 02, can we always omega extend to a model of RT22? This is the remaining question. So this, you see, this negation of an induction axiom appears very naturally here. Okay, when we try to understand the logical strength of RT22, we know something. If we have a lot of induction, we know what to do. So what remains? We really want to look at theories that have a negated induction axiom inside. Okay, so this is, I would say, why my co-authors started looking at these theories. I have induction at one level, but not at the next level. What should we do? They want to know more about the logical strength of RT22, so they started looking at these theories. But at the moment, I believe this is still open, this question in general. So let's look at a case when these omega extensions tell us more about the theory. This is about the weak Konig lemma. Probably many of you know this pretty well, but anyway, I'll remind you of what the weak Konig lemma, the theory WKL0 star do. I have one sentence here which is intended to say that B sigma 1, if we look at B sigma 1 plus X, this is a first order theory. The second order counterpart of it is WKL0 star. So this is one of the model theoretic meaning of WKL0 star. And what I mean by this is that, let's say I take a model of I sigma 0. Then I look at just any initial segment that is closed under exponentiation. So closed under exponentiation. Then any such initial segment will have to satisfy B sigma 1 plus X. As an L1 structure. It will have to be an L1 structure, and it will satisfy B sigma 1 plus X. And conversely, if you have, say, a countable model of B sigma 1 plus X, then it is a proper initial segment of a model of I sigma 0. So really, B sigma 1 plus X is precisely the first order theory of exponentially closed initial segment in a model of I sigma 0. And there is a second order counterpart of this. Say, if we look at such an initial segment, naturally, this initial segment has a second order part that is given by the big model. If you look at all the subset of the initial segment that is coded in the big model, that gives you a structure for second order arithmetic, and this satisfies WKL0 star. Well, it always satisfies WKL0 star, and whenever you have a countable model of WKL0 star, then it's realized in this way. There's an exponentially closed card that is the number universe of your model, and the second order part is precisely the coded subsets in the big model. So WKL0 star is precisely the second order theory of exponentially closed initial segments in models of I sigma 0, say. This is one of the model theoretic meanings of WKL0 star. There are other meanings of it. We may, if we have time, maybe we'll see another one in a moment. I think recursion theoretically, this WKL0 star, you can phrase it in terms of Scott sets, PA over another set, etc. The actual definition is, firstly, it has I sigma 0, 0 plus X, a little bit of induction. Then it has delta 0, 1 comprehension, which just says what you think it says. Any set of numbers that is both sigma 0, 1 definable and pi 0, 1 definable is in the set universe. And an axiom stating WKL, the weak Konig lemma, which says every unbounded 0, 1 tree has an unbounded path. The first thing to note is that WKL0 star proves B sigma 0, 1 plus X. Note that in the definition of WKL0 star, I only have I sigma 0, 0. This is weaker than B sigma 0, 1, but with the other schemes, with the delta 0, 1 comprehension with WKL, we are able to get a little more induction out of it. Actually, you can prove the B sigma 0, 1 using delta 0, 1 comprehension. You can also prove the B sigma 0, 1 using the weak Konig lemma. You get two different proofs of it. And actually, WKL 0 star is not much stronger. It is pi 1, 1 conservative over B sigma 0, 1 plus exp. And traditionally, this is proved using omega extensions. Every countable model of B sigma 0, 1 plus exp has an omega extension to a model of WKL 0 star. Note that, remember, in general, for the pi 1, 1, for the preservation theorem, for pi 1, 1 formulas, we need recursive saturation in the smaller model. Here, the model need not be recursively saturated, but we are still able to omega extend our model. So this is a nice case where we do not need recursive saturation. The proof of this is forcing. You take a tree that you have in the model that is unbounded, you shrink it by forcing so that you have a path left. You only have a path left. And in the process, you can preserve the induction that you already have, and you iterate this, you get a model of WKL. So this is sourcing in the style of Jokush and so. As a corollary, remember our preservation theorem for pi 1, 1 formulas. As a corollary, B sigma 0, 1 plus X proves all the pi 1, 1 consequences of WKL 0 star. But I'm stating here something a little stronger. I'm saying that B sigma 0, 1 plus X axiomatizes the pi 1, 1 consequences of WKL 0 star because B sigma 0, 1 plus X itself is a set of pi 1 to sentences. Pi 1, 1 actually, sorry. It's a set of pi 1, 1 sentences. And it proves all the pi1 consequences, and it is itself provable from WKL0 star. So it axiomatizes all the pi1 consequences of WKL0 star. Okay, so any question at this point? This is my preparation known results about Konig lemma that I used to prepare for the main theorem. Okay, no at the moment. So what am I going to talk about next? So let's look at the Simpson-Smith result. The Simpson-Smith result tells us that every countable model of B sigma 0, 1 plus X has an omega extension to a model of WKL0 star. It doesn't tell us as it is how many omega extensions it can give us. Okay, actually it is possible that we can find a model of, let's say if it has I sigma 0, 1, then there will be uncountably many. There'll be uncountably many omega extensions to a model of WK0 star, uncountably many theories of omega extensions satisfying WKL0. Actually WKL0, but I can put WKL0 star there. So it's possible that you have lots of omega extensions satisfying WKL0 star. But this is the case when we have I sigma 0, 1. Remember, we talked about the variety of omega extensions a moment ago. If we're at the level I, but not the next B, then there are lots of omega extensions. Here, it is possible that we are not at that level. It's possible that we are at the level of B sigma 0, 1, but not I sigma 0, 1. In that case, we expect that there aren't that many omega extensions. And that is true. And that is the main model theoretic lemma we use to prove our quantifier elimination result. Whenever we are at this level, B sigma 0, 1 plus X plus not I sigma 0, 1, then the previous theorem tells us that we can omega extend to a model of WKL0 star. But this theorem tells us that no matter how you omega extend, you will get an isomorphic model. So all such omega extensions are the same up to isomorphism, well, as long as they are countable. So this is consistent with what we saw about this level, B but not the next I, not many omega extensions. In this case, actually one omega extension up to isomorphism. And this will help us prove the quantifier elimination result. And the proof, I will not talk very much about the proof. I will just say how it goes. It's a back and forth argument. What we do is that we start with a model of B sigma 0, 1 plus X plus not I sigma 0, 1. And suppose that I have two omega extensions that both satisfy WKL0 star. Then I try to build an isomorphism between these two omega extensions. It is not required in the theorem, but actually in the back and forth, we can fix any fixed number, finite number of parameters from the ground model in the isomorphism. So it is just, well, I would not say usual back and forth. It's but it originated from some other kinds of back and forth constructions that people have used in first order arithmetic, and there are some new ingredients from second order arithmetic as well. Okay, so because of time, I will not talk much about the proof except one comment is this final part. I would just like to mention where B sigma 01 is used and where WKL 0 star is used. Okay, B sigma 01, it is a well-known fact that B sigma 01 tells us that if I have a bounded quantifier in front of a pi1 formula, let's say this is delta 0, then this is equivalent over B sigma 01 to a pi1 formula. Okay, this is one of the places where we use B sigma 01. And we use WKL 0 star in a similar way. With WKL 0 star, we know that if I stick a set quantifier, say existential set quantifier in front of a pi1 formula, it is equivalent over WKL to a pi1 formula. Okay, so this is the way where WKL is used in this argument. So you see another sense in which the B sigma 01 and WKL are counterparts of each other in a sense. And this also, in particular, this also says that why I am restricting to B sigma 01, not I sigma 01. If I forget about the second order stuff, I forget about the set universe, I only look at the number universe, then this thing about closure of pi n plus 1 formulas under bounded quantification, this works for B sigma n plus 1 for any n. But this does not work for WKL at higher levels. So there are higher level versions of this for the first order part, but it doesn't work for the second order part. If I prefix a pi 10 formula with a set quantifier, I cannot expect it to be first order anymore. Okay, these are the comments. Let me carry on. Are there any questions or any comments? Anyone want me to say a bit more about this? Okay, no, then what next? We prove this theorem. Well, this is a nice model theoretic theorem, but what we use this for is to prove our quantifier elimination theorem. And what we do is that one way of proceeding is that we look in a classic model theory text. I think this one is from Marcus' book. Then you can use more or less exactly the criterion for quantifier elimination to prove our main theorem from the model theoretic lemma. So what does it say? It says that a theory, well, this is a usual model theoretic lemma. T is quantifier elimination if this thing is true whenever I have a common substructure of two models of T. Then with parameters from the common substructure, the two models of T have satisfy the same existential formulas. So whenever I have a common substructure of two models of T, then these two models satisfy the same existential formulas. This triangle looks familiar. We just saw this triangle on the previous slide. If I have a common substructure of two extensions that satisfy the theory that we're interested in, and we are able to show that these two extensions satisfy the same existential formulas. Well, in our case, we actually know that the two are isomorphic modulo parameters from the ground model. So definitely they satisfy the same existential formulas over the ground model parameters. So by this pretty standard model theoretic fact, we can deduce from a main theorem that we have quantifier elimination. Except that in the standard result, we have arbitrary extensions. It's just substructure. It doesn't say what kind of substructure. But in our model theoretic lemma, our extensions are always omega extensions. But it doesn't quite matter because we had this preservation theorem for pi11 formulas. If the models are sufficiently saturated, say countable recursively saturated, then all the extensions that we want to exist to prove this usual standard model theoretic lemma, we can replace those extensions by omega extensions. So that gives us the quantifier elimination result, which says every L2 formula is equivalent to an arithmetical formula over this theory, WKL0 star plus not I sigma 0, 1. And as I said, the proof is you run the proof of this standard model theoretic lemma, not on arbitrary structures, but on countable recursively saturated structures, so that our extensions are omega extensions. So this is how we got the quantifier elimination. We do some model theory, some back and forth, and we squeeze out some quantifier elimination. But as is usual in model theory, if we use this method, it doesn't explicitly give you a quantifier elimination procedure. So if you give me a formula in the language of second order arithmetic, which arithmetical formula is it equivalent to under this theory? We have some other method of telling how to do this quantifier elimination explicitly. So over the appropriate theory, when is it true that this L2, well, when is this L2 formula true? This L2 formula is true precisely when this L2 formula is forced. And forcing here, we are using the notion from Jokuchen, so that we saw 2 slides ago, when it was used by Simpson and Smith to prove the conservativity of WKL over B sigma 1 plus X. So we force with infinite trees. If it is forced, then it is true, and it's true is forced, because by the isomorphism theorem, there is only one omega extension. So no matter how you force, you're going to get the same thing. So that is the idea behind the proof. And this is arithmetical because I just restrict everything to the sets that appear in the formula, plus possibly a set in which the induction fails. Okay, so this gives us an explicit way of eliminating quantifiers. When is this L2 formula true? Is exactly when it is forced and it is arithmetical. Okay, so this is a place we have quantifier elimination. Then we can open any mainstream model theoretic book and see what consequences we have from quantifier elimination. One of the things we have, well, firstly, how can we apply the results? In a sense, we treat the arithmetical formulas as quantifier-free, pi11 formulas as universal, pi12 formulas as A2 or AE formulas. Then we see what the textbooks tell us. One of the things it tells us is that there is a model theoretic meaning of WKL that I mentioned in the abstract. I think it realizes as the model companion of B sigma 0, 1 plus X plus not I sigma 0, 1. And what does it mean? The usual meaning of a model companion is that it has to be model consistent with the original theory, and it has to be model complete. And this is precisely the analog of those two conditions in the context where we have this conversion of arithmetical into quantifier-free, etc. So model consistent means that the two theories have the same pi11 consequences in this case. And model completeness usually means every universal formula is existential. So in this case, every pi11 formula is sigma 1, 1, which we know is true because with quantifier elimination, not only that all the pi11 formulas are sigma 1, 1, but they are arithmetical. So model complete and model consistent, and the usual results in model theory will tell us that given one theory, this, let's say B sigma 0, 1 plus X plus not I sigma 0, 1, there is a unique theory. Well, if there is one, there is a unique theory that satisfies both of these conditions. So WKL naturally arises in this way. If we have B sigma 0, 1 plus X plus not I sigma 0, 1, there is a canonical theory that grows out from this, that is the model companion, and that is WKL. That's the model theoretic, one of the model theoretic meanings of WKL in this context. In the title, I wrote model completion instead of model companion. Model completion is just a stronger form of model companion in the sense that we do not only have model completeness, but we have quantifier elimination. So model consistency plus quantifier elimination is model completion. We have something stronger in the context, but to get a unique theory satisfying two conditions, model companion is enough to get a unique theory satisfying this. And such a result is not achievable without including some negated induction action, because it is well known that there is a pi11 formula that is not sigma 1, 1. That's provable in AZA0. In particular, it is true in the true model of second order arithmetic. So without including something that is false in the theory, you cannot get model completeness. So hopefully that motivates you in looking at negated induction actions. Another consequence of this model companion result is that it's a standard model theoretic fact that if a theory has a model companion, then you can look at the models of this model companion. These are precisely the existentially closed models. So here we have a model companion. So the models of this model companion, this WKL0 star plus not I sigma 0, 1, are precisely the existentially closed models of the theory. And existentially closed in this sense, in this case, is just sigma 1, 1 closed, meaning that it satisfies. There is a proper definition here, but intuitively, they just satisfy as many sigma 1, 1 formulas as they consistently can. So these models of WKL0 star, in the presence of the negation of I sigma 0, 1, they are very rich models again. Okay, so this is what the general model theory tells us. It also tells us, or it tells us, yes, but we can reformulate all these and see what it tells us about the reverse mathematics. So all these originate from the reverse mathematics. We can talk about pi11 conservativity, for example. What does it mean for a sentence to be pi11 conservative? Let me just remind you of this. A sentence sigma is pi11 conservative over this theory if and only if adding this sentence doesn't help us prove more pi11 sentences. This is what it means for sigma to be pi11 conservative over the theory. From the quantifier elimination result, the model theoretic lemma, we can have this equivalence, this criterion for pi11 conservativity over this theory, B sigma 0, 1 plus X plus not I sigma 0, 1. And this is true precisely when this sentence is provable from WKL0 star plus not I sigma 0, 1, proves this sentence. We saw from Simpson-Smith essentially that WKL0 star plus not I sigma 0, 1 is pi11 conservative over the theory, over B sigma 0, 1 plus X plus I sigma 0, 1. So this tells us that WKL0 star is the strongest pi11 conservative pi12 sentence over our theory, which usually doesn't happen for second order arithmetic. or for arithmetic in general. So we want to apply it to some theories which tells us which, let's say we are interested in whether RT22 is pi11 conservative over the theory. So according to this corollary, what we can do is we try to see whether it's provable from WKL0 star plus not I sigma 0, 1. And in fact, this is true. It is not provable from this theory. RT22 is not provable. So by our corollary, we know that RT22 is not pi11 conservative over this base theory, B sigma 0, 1 plus X plus not I sigma 0, 1. But I'd say in this particular case, as we had before, this model theory doesn't help us very much in understanding RT22, because how did we prove this non-provability result? Is that we produced a sentence that is proved, that can be proved in RT22, but cannot be proved in the other theory, WKL0 star plus not I sigma 0, 1. And this sentence is actually pi11. So this particular pi11 sentence, which separates WKL0 star from RT22, is actually also what we can use to separate B sigma 0, 1 plus X plus not I sigma 0, 1 plus RT22 with the theory without RT22. So if we have this sigma, then we know that it's not pi11 conservative anyway. So the corollary doesn't quite help, although it's still pretty nice. It reduces, well, one of the consequences is that it reduces in this particular case, this pi11 conservative problem, which is a pi2 problem, into a provability problem, which is sigma 1. So pi11 conservativity is pi2, but provability is sigma 1. If we do not have the negation of induction, then this is not achievable. If we just remove negation of induction everywhere, the problem is pi2 complete, but here we can reduce to sigma 1. And another thing, this is model theoretic, maybe you are less interested, so I will maybe skip this because I think I'm running out of time. So I'll just end, just go to the last slide and say that we've seen a lot of nice things that usually you do not see in the model theory of arithmetic. And this is only achievable when we have the negation of an induction axiom in the theory. So I hope this demonstrates at least partially this insight from K that if we want to understand the model theoretic property of a model of arithmetic, it's useful to look at what induction axiom that the model does not satisfy. So it is not entirely pointless to look at negation of an induction axiom, and it gives some nice model theory as well. Thank you. So I'll end here. Thank you. Any questions for me?
Thanks, Lok. I have a question. Could you please go back to the slide where you proved your main theorem?
Main theorem. Yes, this
no,
one.
The other one, like the one after this.
This one.
Yeah, that's right. Yeah. So you might have explained it, but I missed it. So why, like, what's the connection between recursive saturation and saying that all extensions can be assumed to be omega extensions? Is there a basic fact here that I'm missing?
It is that, what do I have? Is here. So the first lemma here says that if you have the right omega extensions, then you have the right theory. but the converse is not quite true. If you have the right theory, you may not have the right omega extensions except when you are recursively saturated.
I see. Okay.
Yeah.
Okay, I'll have to work out the, the logic in my head, but yeah, thanks. I had another question, which is, so so you showed kind of two kinds of phenomenon here, where in one case, I forget what the assumptions were, but in one case you get uncountably many omega extensions, which are not even elementarily equivalent, right?
Yes.
Not wrong, that's what you said. Yeah, and then on the other hand, you get a situation where the extensions are isomorphic.
Yes.
Yeah, so have you encountered situations where you get something in between, like you have extensions which are elementarily equivalent but not isomorphic somehow?
Elementarily equivalent but non-isomorphic. I think.
Hopefully that's not a stupid
yes.
question.
No, that's not a stupid question.
Okay.
At least for theories that are weaker than PA, I don't remember anyone looking at that question, but for models of PA, I think there were people who looked at this, and I was not one of those.
Okay.
But I remember there are those results. But at PA, you don't look at the theories, but maybe you look at the theory of a model with a cut or something like that. And you look at how many theories you can have with the pair, the model with the cut, how many theories you can get. I think there are, let's say, so what I have is maybe should I change? Maybe I'll just write here. I'm not writing a lot. So if I have a model of PA and then I look at a cut, I of M, then I look at how many theories there are in this pair.
Ah, okay.
Then depending on what condition you put on the cut, let's say if I want the cut, the pair, so I want the pair Mi to be recursively saturated, then there are only countably many theories. So many of them will have to have the same theory. So that's the opposite of what you want. You want the same theory, but not isomorphic.
Right.
Yeah, I think there are such results in this context with a model with a cut, but I don't remember it appearing in other contexts, in models of arithmetic at least.
Okay, yeah, thank you very much.
Okay, thanks, Jinla. Other questions?
So, Tila, so what is the natural generalization of your theorem for B sigma n bigger than 1, rather than relativization of WKL star to that? For example, if we look at B sigma 2, B sigma 3, B sigma 2, do we just look at the full WKL, or do we have something else that can also give us this similar result?
If you're talking about the isomorphism theorem, where is it? The isomorphism theorem, as I mentioned at the end, I stated it at the level of B sigma 0, 1 and not I sigma 0, 1, not only because it's simpler, but it's because here we use WKL in the way that it tells us that the pi1 formulas are closed under set quantification. But if I change pi1 to pi10, then it shouldn't hold, as far as I know. So the second order part does not generalize to higher level. At least the proof doesn't generalize to higher levels. If we only look at the first order part, if I have a model of B sigma 10, but not I sigma 10, then there are similar results, but it's less interesting because there are no sets around. So you're just making an automorphism of the model, which is useful as well. As you know, it can prove some pigeonhole principle at that level. But otherwise, I don't see, apart from this nice model theoretically, I don't see any other applications.
Okay, thanks.
Thanks.
Any other questions? All right, if not, let's thank Tim Lok again. Thank you so much. Really nice talk.
Thank you very much for coming again.